I welcome you all in this course on mechanical measurement systems. And today's session will be on problem solving. We will solve a few numerical examples based on statistical analysis of experimental data. So, we will start with example number 1, which states that to measure the stiffness of a cantilever beam, a gravity force 10 Newton was applied at the free end of the beam and the resulting end deflection was noted by a dial gauge. So, there is a cantilever, it has one fixed end and one free end. On the free end, the load is applied of 10 Newton and deflection is measured with the help of dial gauge, right? And stiffness has to be measured. So, stiffness is delta by F, deflection per unit force. And sorry, here it's not stiffness, deflection has to be noted. So, deflection delta has to be noted using a dial gauge, right? The plunger of dial gauge exerts a force of 0.12 y plus 0.25 n. So, plunger causes a force 0.12 y plus 0.25 Newton. 0. Right. So, this is y is the deflection in vertical direction, right. So, this is a sort of relation between force and deflection of the dial gauge. When beam is in initial horizontal position before the application of load, the gauge deflection is 2 mm, right. So, gauge is installed somewhere here and stylus, so very close to this, just very close to the load, right, and initial deflection is 2 mm. So, xi is 2 mm. So, dial gauge is already compressed, initial deflection means it is already compressed. So, when the cantilever will go down, the compression in the dial gauge will be relaxed, right. So, this is how it is done. When beam is in initial horizontal position before the application of load, the gauge deflection is 2 mm. Calculate the percentage error in the measurement of deflection in free end of the cantilever due to influence of dial gauge, right. So, because dial gauge is compressed initially, so it is also exerting certain force on the beam and this will disturb the original deflection. So, first of all, true deflection, let us calculate true deflection of the beam. So, in a cantilever beam, y is equal to W L Q by 3 EI. This is formula for calculating the deflection, right. Now, here W instead of W, let us take F. So, y by f for this cantilever is going to be LQ by 3 EI. Now, the length of the cantilever is 250 mm and cantilever has certain cross section area, it has a rectangular cross section area and this is by 20 mm by 5 mm, that is the cross section of the cantilever. And the module of elasticity is 200 gigapascal, because we will be using these values here. So, here we can find that 0.25 cube divided by 3 into 200 into 10 to power 9 into I. I is, so it is 20. So 0.02. Just a minute. We can further simplify this. This is L cube by 3E. Now I is BD cube by 12. So BD cube by 12. And this is 3, so this will be cancelled out 4. So we will be getting 4 L cube by E BD cube. Now here we can put the values. 4 into 0.250 cube divided by 900. The value of E is, sorry, 200, not 900. 200 gigapascal, so 200 into 10 to power 9 multiplied by B. B is 0.02 if you convert this into the meters, and 0.5 mm, so it is 0.005 cube. Now this will give the value of y by fs, if you simplify this, is going to be 1.25 into 10 to power 4 minus 4 meter per Newton, or we can say 0.125 mm per Newton. So y by f for load we have calculated. So y by f for this load is 0.125 mm per Newton. Fine. Now, with the help of this, we can always calculate the value of delta. Delta is this multiplied by the load. So if we want to have delta, true value of delta, so delta is 0.125 multiplied by load, it is 1.25 mm. It is as simple as that, right? Now, total load on this, the load is on this cantilever is not due to this concentrated load, but also by the stylus of the dial gauge. So the total load is F is equal to 10 Newton, this is by this, plus 0.12 2 minus yi plus 0.125. Yi is the modified deflection, because when the cantilever goes down, sorry, yes, it is not 125, it is 0.25. Because when the cantilever is deflected, the stylus of or the spring of the dial gauge is relaxed. That is why we have taken 2 minus yi, right? Now F is, again we can calculate 10 plus 2 for 0.49 minus 0.12 yi, or we can say F is equal to 10.49 minus 0.12 yi. This is modified force. This is modified force. Now, if we want to calculate yi, we have this value. So, if you want to calculate yi, it is F multiplied by 0.125. Because we already have this y by f. So simply we multiplied f, we replaced f by yi. So we simply yes. So in order to find yi, we simply multiplied this f by 0.125. So we simply just f, this is multiplied by 0.125, and we are getting. Now we can solve this, and this will give yi as 1.3125 minus 0.015 yi, or yi is equal to 1.292 mm. Initially it was 1.25 mm. Ideally it should have been, but due to loading, this is also a loading effect, as we discussed earlier. The stylus is a primary sensing element, so this is also causing the loading effect, and due to this loading effect, the deflection has increased from 1.25 to 1.292 millimeters. Now, if we want to have error in the measurement, now error in the measurement is measured value minus true value. Measured value is 1.292, true value is 1.25, right? So, the error in the measurement is 0. What is that value? 1.292, 1.242, 0.242. .042, okay, is equal to 0.042 mm. This is error in the measurement. And if you want to have percentage error, then divide this is equal to 0.042 divided by 1.25 into 100, and that will give the error in the measurement as 3.36%. So, error in the measurement of deflection in cantilever by measurement with the help of dial gauge is 3.36%. Now, after this, we will take one example on uncertainty in measurements. Now, a resistance arrangement of 50 ohms is required. A resistance arrangement of 50 ohms is required. Which of the following two arrangements shall have minimum uncertainty? 25 plus minus 0.02 ohms. We have two resistors of 25 plus minus 0.02 ohms and two resistors of 100 plus minus 0.1 ohm. We have these resistors and we have option. We can have 15 ohms by putting these 25 in series. So, R1 and R2. So, R is equal to R1 plus R2 is equal to 25 plus 25 is equal to 50 ohms. Or we have option that instead of putting these 25 ohms in series, if we put 100 ohms in parallel, 100 ohms in parallel, that is R1 and R2, then 1 by R is equal to 1 by R1 plus 1 by R2 is equal to 1 by 100 plus 1 by 100 is equal to 1 by 50. So, R is equal to 50. Now, the issue is which of these two arrangements will have minimum uncertainty, right? So, we will start with the basic formula for uncertainty measurement. So, for addition formula, R is equal to R1 plus R2, right? So, del R by del R1 is equal to 1, del R by del R2 is also equal to 1, both are 1. So, error in the measurement of R1 is del R by del R1 by UR1 whole square plus del R del R2 UR2 whole square raised to power 1 by 2. Now, here because these have one value, so error in the measurement of R1 is equal to uncertainty in R1 0.02. right? So 1 into 0.02 whole square plus 1 into 0.02 whole square raised to power 1 by 2. And when we further solve it, we get error of 0.02828 ohms. That is the error when loads are connected in series. So let us assume R series is 0.02828 ohms. Now the second case. Now the second case is when the resistors are connected in parallel. When resistances are connected in parallel, then 1 by R is equal to 1 by R1 plus 1 by R2. Or R is equal to R1 R2, R1 plus R2. Or we can say R1 R2, R1 plus R2 raised to power minus 1. Right? So now we can take del R by del R1 is equal to R2, R1 plus R2 raised to power minus 1. Differentiation of this multiplied by this, differentiation of this multiplied by this. Right? So minus, this is R1. When we differentiate it, this is minus 1. So that is why minus is coming here. And R2, R1 plus R2 raised to power minus 2. Fine. Now we will put the values 100, 200 raised to power minus 1, minus 100 into 100, 200 raised to power minus 2. And this will give the value as 0.25. Right? So here we will write del R by del R1 in case of parallel is 0.25. Now again same exercise shall be done for R2. And R2 also, if you look at the values, R2 you are also going to get the same value. So del R by del R2 is also 0.25. Right? And now error in R, del R by del R1, uncertainty in R1 whole square plus del R by del R2, uncertainty in R2 whole square raised to power 1 by 2. Now here again uncertainty is 0.1, right? So 0.25 into 0.1 whole square plus 0.25 into 0.1 whole square raised to power 1 by 2. And when we solve it, we get uncertainty as 0.0353. So error in the measurement or uncertainty in the measurement, uncertainty of R. Uncertainty in the measurement of R is when they are connected in parallel. 100 ohms are connected in parallel. It is 3.535% or 0.03535, right? And when they are connected in series, it is 0.02828 ohms. So definitely this is the better way of getting 50 ohms resistance because error is lesser comparison to the parallel arrangement. So this is about the uncertainty. Now I will take up one more example on chi-square test. This example reads, there are two dices. So I'll first rub it off, then we'll discuss about this. there are 2 dices, okay? So each dice has 6 faces, right? And they are rolled 200 times. They are rolled 200 times, right? And 200 times the results are given in table. I'll draw the table. Calculate the probability that the dice are unloaded. Unloaded means there is no unbias in the dice and it is following the right trend. If dice has unbiased, then probability of, say, for you are rolling one dice and it has bias. So probability of getting one figure is more than probability of getting another figure. So here we have to ensure that there is no issues regarding the dice. It is not loaded, it is unloaded, or the trend is the right trend. The trend which we are getting out of 200 of samples is the right trend. So the number we will draw, first of all, I will start from the top. So 1 we cannot get in 2 dice. So we will start with the 2. So 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. So whenever we throw the 2 dices, we will be getting these numbers. Addition of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 10, 11, 12. So we'll be getting number out of these 11 numbers. Now we have thrown dice 200 times and we have got the frequency 9, 9, 15, 18, 26, 27, 36, 26, 12, 14 and 8. Right? So in order to avoid any confusion, I will draw the horizontal lines. Okay. Now, this is the actual data we are getting, observed value. Now, what should be the actual value? Ideally, how many times the 2 should come? Probability. First of all, we will find the probability. What is the probability of getting 2? Combination of 1 and 1. So, and total combinations are 36. So, it is 1 by 36. Probability of getting 3. Probability of getting 3. 3 we can have how many combinations? We can have 2 combinations. 2, 1 and 1, 2. Okay, so dice 1, 1, dice 2, 2 and 2, 1. So 2 by 36. 2 by 36 is 1 by 18. Right? So we'll further extend these lines otherwise. Right? Now what about third one? 4. How many combinations we have? 4. 4, 2 plus 2? 2, 2, 3, 1, 1, 3. So 1 by 12. Because 3 by 36 is 1 by 12. Then 5. How many combinations for 5? 4, 1, 1, 4, 3, 2, 2, 3. 4. So 1 by 9. So likewise, we'll write probability of each and every 5, 6. 6 is 5 by 36. 7 is 1 by 6. 5 by 36. 1 by 9. 1 by 12. 1 by 18. And 1 by 36. So 7 has the highest probability. Here 7 has the highest probability. And followed by 8 and 6, right? Now this is the probability. Total number of throws are 200. So if you multiply probability by 200, that is a true value, expected value, right? So expected value is going to be, this is, okay, this is expected value. So this is a probability. And expected value will be probability multiplied by 200. So if we multiply this by 200, we will be getting the expected as 5.6 11.1, 16.7, 22.2, 27.8, right, 7, 33.3, 27.8, 22.2, 16.7, 11.1, 5.6. So these figures we have got just multiplying probability with the 200. So this is the expected value. It means the expected number of times phi will appear is 22.2, though practically it is not possible. Either we will have 22 or 23. But frequency has to be 22.2, but we are getting only 18. For let us say 7, it should have been 33.3 times, but we are getting 7 only 27 times. Now these are the observed value and these are the expected values. Now we can simply do the chi-square test. Now in order to chi-square test, simply we have to calculate the value of chi-square, right? And it is a, again, sum of, if you remember, I is equal to 1 to I is equal to n, observed value minus expected value whole square divided by expected value raised to power 1 by 2, right? And when we do for all these, I will not go into the detailed calculation because it is simple arithmetic. You will be getting the value of chi-square as 11.03. Right? Now regarding the degree of freedom. Now degree of freedom, here there are total how many? 12. 12 minus 1, 11. So there is only one restriction, that number of trials are, these numbers are restricted. So f is equal to n minus k, 11 minus 1, 0. Sorry, 10. So for degree of freedom 10, this square, let us find out the probability. And once we look at the chart for 10, right? So for 10, it is 11.03. So it is between it is between 0.5 and 0.25, because at 0.5 it is 10.3, 0.5 the probability is 10.03, 10.3 and 0.025, sorry, 0.25 and 0.25, it is 12.5. So P, and this is the value of chi-square. So definitely this will lie in between these two values. So these values, these numbers, they are following the right trend and there is no bias in the dice, right? Now after this we can take one more example, that is about, again related with the heat transfer. Now in this example there is a cylinder having the volume of 2 meter cube. There is a cylinder having the volume of 2 meter cube, that is given. Which has a certain pressure and temperature. There is certain pressure is not known, and certain temperature, gas is filled. And there is a dial gauge on the cylinder which reads pressure with 1% accuracy and temperature at 2% accuracy of true value, of the displayed value. So there is a cylinder, and on the cylinder it has pressurized gas, and there is a dial gauge which shows the pressure, and the accuracy is 1%, and temperature sensor is also fixed, which has the accuracy of 2%. I mean 2% of error in the measurement, and pressure gauge has 1% error of measurement. Estimate the permissible uncertainty in the weight so that uncertainty in determination of R does not exceed 3%. Right? So that is in R. So pressure vessel has certain gas filled at a certain pressure, filled at certain temperature. Error in the maximum possible error in the measurement of pressure is 1%, maximum possible error in the measurement of temperature is 2%. We have to determine the value of R. So what we can do, we can weigh this cylinder. Now permissible error in the measurement of cylinder weight or mass is required so that the uncertainty in the measurement of R is not exceeded 3%. So simply we will use R is equal to, M is equal to PV over RT. That is ideal gas equation. So R is equal to PV by MT. Now we have to find uncertainty in the measurement of R. So uncertainty in the measurement of R is del R by del P is equal to V by MT. Del R by del V is equal to P by MT. Now again, del R by del M, because R is equal to PV is equal to RT. Sorry, R is equal to PV is equal to MT, PV by MT. So when we say del M, then it becomes PV over T minus 1 by M square. And del R by del T is equal to PV by M minus 1 by T square. Okay. Now, uncertainty in the measurement of R is going to be equal to del R by del P, error in the measurement of P, whole square, plus del R by del V, error in the measurement of V, whole square, plus del R by del M, error in the measurement of mass, whole square, plus del R by del T, error in the measurement of T, whole square, and raised to power 1 by 2. Now, error in the measurement of pressure is not known, but delta P by P is known to us, right? So, so we can always take uncertainty in the measurement of R divided by R. Now, both sides are divided by R, right? Now, this side, if you take this side, delta R over delta P is equal to V by MT. Divided by R, it is going to be PV by MT. So, here MT will be cancelled out, V will be cancelled out, and we will get this error in P divided by P whole square. Similarly, here we will get error in V divided by V whole square, and similarly here we will get error in M divided by M whole square and error in T divided by T whole square raised to power 1 by 2. Because the whole expression is divided by PV by MT. right? And now, if we further simplify this, we will be getting uncertainty in R divided by R, let us say it is whole square, then is equal to this error in, or uncertainty in P by P whole square, or let us take, okay, plus uncertainty in V by V whole square, plus uncertainty in M by M whole square, plus uncertainty in T by T whole square. Now, this is uncertainty in the measurement of R is 3%. Permissible uncertainty in the measurement of R is 3%. So, it is 3 square is equal to, this is 1%, so 1 square plus volume. Volume is given, I mean, volume is not measured, so this is going to be 0. This is going to be 0. Uncertainty in the measurement of mass we have to find out. Uncertainty in the measurement of temperature is 2%. So 2 by, so 2%. Okay. We are not divided by 100 because both sides will be dividing by 100 square. We will getting the same values. So now uncertainty in the measurement of mass whole square is equal to 9 minus 1 minus 4 is equal to how much? 4. Or uncertainty in the measurement of mass is plus minus 2%. Error in the permissible error in the measurement of mass is only 2%. So a cylinder, if you want to find the gas constant R for a gas using the ideal gas equation P is equal to RT, MRT, then error in the measurement of pressure is 1%, error in the measurement of temperature is 2%. If you want to restrict the determination of R by 3%, error in the measurement of mass should not exceed 2%, right? That is all for today. From the next class, we will start with the dynamic response of measuring systems. Thank you.